this is where you need that periodic table next to you, and you need your calculator. So first of all, let's just review what is a mole, right? So like, what is a mole? We've talked about it. You've talked about it in your previous chemistry course. So a mole is the amount of a substance that contains as many things as there are in 12 grams of carbon 12. So a mole of anything is 6.022 times 10 to the 23rd. And we call this Avogadro's number. So what does it mean? It's just like I call it like a giant dozen, right? So like if I said a dozen eggs, you'd be like, oh, 12. If I said a dozen donuts, you'd be like 12. If I said like a dozen people, you'd be like, I got it, Dr. M, 12, right? So when I say the word dozen in your brain, you think 12, right? Well, when I say mole, you should think 6.022 times 10 to the 23rd. So if I say how many eggs are in a mole, you're like, oh, 6.022 times 10 to the 23rd. Okay, how many donuts are in a mole? 6.022 times 10 to the 23rd. How many people are in a mole? 6.022 times 10 to the 23rd. So it's just like a new like definition of like abbreviated. Like I say dozen, you think two. I say pair, you think two. I say dozen, you think 12. I say pair, you think two. I say mole, you think 6.022 times 10 to the 23rd. And so that's what a mole represents. Now, the molar mass is the mass of 1 mole of anything in grams, right? So it's the mass of anything in grams. And so sometimes this can be kind of tricky, and we'll just keep developing this one. So how many things are in a mole? 6.02 times 10 to the 23rd. The molar mass is how much those things weigh, right? So if you have 6.02 times 10 to the 23rd of something and you put it on a scale, that's what we call the molar mass, because it's the mass of a mole, hence molar mass. So how many things? 6.02 times 10 to the 23. You weigh that, that's the molar mass. So if we talk about carbon, which is kind of how I always call this like a geometry proof, like chemists and physicists like use this geometry proof. Remember, like if then, this is kind of a geometry proof, I call it. So what they said is if we're talking about carbon 12, 1 mole of carbon 12, remember a mole of anything, 6.02 times 10 to the 23rd of it. So if you put that on a scale, it weighs 12 grams. And so then they made this definition. They said, okay, well, 1 atom weighs 12 AMU. A mole of atoms weighs 12 grams. Okay, so what is the difference between this and this? This is a single atom, 1 single carbon 12 atom. If I said next week in lab, hey, could you go get me a carbon 12 atom and tell me the mass? You would be like, no, right? We don't have the capability to do that. That would be insane. But if I asked you to get a mole, you could do that because like, oh, you're like, I know a mole weighs 12 grams. So using our periodic table, so if we have a periodic table, this is lithium, and I think lithium's atomic number is 3. So 3. And then 6.941, and that is the molar mass of lithium. So that's how much 6.02 times 10 to the 23rd atoms of lithium weighs. So for our purposes, atomic mass, that's an atom or a molecule, not usable for us. So we use grams, molar mass in grams, and that just means we've got a mole of them. So let me just explain this just a little bit more. So that is 1 mole of carbon, 1 mole of sulfur, 1 mole of copper, 1 mole of iron, 1 mole of mercury, right? These don't weigh the same, but how many particles? This is 6.02 times 10 to the 23rd atoms of carbon. This is 6.02 times 10 to the 23rd atoms of sulfur. That's 6.02 times 10 to the 23rd atoms. Are you getting this, right? They don't all weigh the same, right? Because they have different numbers of protons and neutrons, right? If it's got more protons on neutrons, it's going to weigh more because the atoms are bigger, right? So if I want to look at this to see if anybody's got their periodic table, which one of these weighs the least of this picture? Which one weighs the least?
Is it carbon?
Yeah, it's carbon. Why? Because if you look at carbon on the periodic table, carbon is 6 and 12.01. You can see the number is the least, it's the smallest on all of them. And carbon 12 has 6 protons and 6 neutrons, right? So the atoms are tiny. And if you look at mercury, which I think mercury is the biggest on here. Mercury is 200.6 and it's 80. And so mercury has like 80 protons and like 120 neutrons, right? It's got more protons and neutrons. So carbon is like this big. So 6.02 times 10 to the 23rd of them don't weigh that much. And mercury is like this big, right? So 6.02 times 10 to the 23rd atoms of mercury weighs a lot more because it's a bigger atom, right? And so, but all of these have the same number, right? It's just like if you had a mole of donuts or like a mole of pencils, well, the donuts should weigh more, especially for jelly donuts, right? Because they're bigger, right? They weigh more. And so a mole of them should weigh more. Okay, so hopefully that kind of like helps you understand what a mole is, because I know a lot of times we hear about it and we're like, I don't know what that means. So hopefully it is getting clearer and clearer. Okay, so now let's look at how we use molar mass. So we're going to incorporate a little bit of stoichiometry while we're doing this. So let's just do potassium. And so if we have, look at our periodic table, here's K 1939.10. So this number on the periodic table means this: 1 mole of K weighs 39.1 grams, right? So, and when we write this, so that's what this decimal number means. It means this. And we can write this many ways. We can write it like this. Or we can write it like this. Or we can write it like this. This is the same as this, is the same as this, is the same as this. All 4 of these things mean the exact same thing, right? So when you see that periodic table, that number is this, this, and this. Any of these is the exact same thing. Now, if we want to go from moles to atoms, again, 1 mole of anything has 6.02 times 10 to the 23rd of it. So we can write this in so many different ways. We can write 1 mole of K is 6.022 times 10 to the 23rd atoms. Or we can say there's 6.022 times 10 to the 23rd atoms in 1 mole of K, right? All of these things are exactly equal to each other, right? And so how do we know which one we're going to use? We want to get rid of the units. So we have grams. So grams are on the top, we need grams on the bottom. So you can see this has moles on the bottom, this has grams on the bottom. We are going to use this one, right? And then our units cancel out. And we want atoms, so moles has to go on the bottom. So we say, okay, well, which one has moles on the bottom? Not that one, that has atoms on the bottom. Aha, that one has moles on the bottom. So we're going to use this one. Another way to think of this is one side goes on the top and the other one goes on the bottom, or vice versa, right? One goes on the top and the other one goes on the bottom, or vice versa when you're looking at these. And so then we put that in our calculator. We think about what should our sig figs be? 3 sig figs. 3 sig figs. Oh, that brings me. You can see the answers to your quiz now, by the way. It's published. Your first quiz. Just look on Canvas. You can see the answers now. Okay, and then remember, when we're doing this, sig figs, units, right? And our answer. Okay, so we're going to keep practicing with this. Keep practicing with these unit conversions. Okay, so molecular mass. Molecular mass is we just add them up from the periodic table, right? So if we have sulfur, sulfur is 32.07, and then oxygen is 16.00. I don't know what sulfur's atomic number is. Sulfur is 16. So we just add these. So you can see we have one S and two O's. So we have one S and two O's. And so we just add, right? And then again, when we do this, an AMU, that just means one sulfur atom and two oxygen molecules. It's not really useful for us. So whatever you get, one molecule weighs this much, but we're going to stick here with moles and grams because we can't use this. It's not useful for us, right? Because we can't do that in the lab. We need grams and moles. So we just add up the numbers from the periodic table. Okay, so let's try one. So this one's a little trickier. So for this one, how many H atoms are in 72.5 grams of C3H8O? So again, you look at your periodic table, carbon is 12.01. That does not look like 12.01. 12.01. Hydrogen is 1.008. So 30. And oxygen is 16.00. If you look at your periodic table, that's what it says. So when you add it up, we have 3 carbons, we have 8 H's and 1 O. So we just multiply those out. So hopefully everybody remembers that, right? And in this, right, we have 3 carbons, we have 8 hydrogens and 1 oxygen in this molecule, right? So we can create another piece to this. So, someone questioned, will I be providing molar masses to save time? Not for your quiz. For the quiz, you have to know you're going to have to add molar masses. And after your first exam, absolutely, I will give you molar masses because once you show me that you know how to do molar masses, it's just you wasting your time adding them, right? Because you just have to add it on your periodic table. So for your quiz and your exam 1, you're going to have to add them. After that, absolutely, I'll give them to you. Okay, now I want you to notice something. Do you see how they're giving us grams of C3H8O, but they're asking for hydrogen atoms? So hopefully you've learned this before. If not, this is a mole ratio. Whenever they're giving you something and they're asking you for something else, you're going to have to do a mole ratio between the two. In chemistry, the only way you can go from something to something else is a mole ratio. Now, what do I mean? This is C3H8O. This is hydrogen atoms. Hydrogen atoms are different than C3H8O. So we need to do a mole ratio between the two of these. Now, how do we do that? You can see there's 8 hydrogens in one of these. So in one molecule, there's 8 hydrogen atoms, or in 1 mole of these, there's 8 moles of hydrogen. And again, where did I get that? Right here, because there's 8 hydrogens in one of these. And I'm going to have to do what's called, again, a mole ratio. So whenever you see grams has to go on the bottom, right? And it's always, if you add it from the periodic table, it's always grams per mole. And then our units cancel. So now is the perfect time, once we hit moles, we can do our mole ratio. And again, one side goes on the top or the bottom, and the other one on the top, vice versa, whichever one you need to do to cross off your units. We've got moles C3H8O. So we're going to put moles of C3H8O on the bottom so we can cross them off. And then look, we've got moles of hydrogen, but we want atoms of hydrogen. So we have to keep going. So we're going to put hydrogen atoms on the bottom. And moles on the bottom and atoms on the top, because we want atoms. And cross off, our units all cancel, which I think I did neatly here, much neater. And we follow our units. So this is why I'm so crazy about your units. It's because it's very difficult to get this question right if you have no units. I mean, maybe you could do it, but you wouldn't be able to do it twice, right? And so when you put this in your calculator, you should get 5.82 times 10 to the 24th atoms. Again, we're going to practice with the stoichiometry a lot. So if you're like, wow, it's okay. Hopefully it's review and you're just kind of dusting off cobwebs. Or if you took intro chem in summer, you're like, oh yeah, I did this 1,000 times. But for the rest of us who it's been a little while, it's okay. It'll get easier. Okay. Now, molecular mass just means molecules. Remember, molecules are two nonmetals. Formula mass means the same thing, or formula units, they mean the same thing. We just technically call that for ionic compounds, but you treat them exactly the same. So if somebody says like formula units or formula mass, think molecular mass or molar mass. It's the same thing. It's just molar mass is technically for molecules and formula mass is technically for ionic compounds. If you interchange them, I don't care. All right. If you interchange them, it doesn't matter to me. But I just want you to know technically you're going to see that formula units which means the same thing as molecular mass, right? Same exact thing. It's just we change the name when we talk about an ionic compound, right? But it's the same thing. So if you interchange the two, I don't care. It's fine with me. Okay, so now for this one I just want to do because it is a little bit trickier. This is 3 calciums, right? 2 phosphoruses and 2 times 4, 8 oxygens, right? So calcium, when you look at the periodic table, is 40.08, phosphorus 30.97, and then there's 8 oxygens. So it's like the distributive property in math, right? So you distribute this 2 to both of these. So it's 2 times 4, so you have 8 O's and 2 P's and 3 CA's. And again, an AMU is the same thing as grams in 1 mole. Same exact thing. So whenever you add it from the periodic table, your units are grams per mole. Okay, so quick little baby review on atomic mass, formula mass. Again, same thing, just ionic compounds are covalent or molecular. Interchange them, I don't care. Okay, next thing, percent composition. All right, so there's not a ton of things you need to memorize in chemistry. This is one of them you don't need to memorize, right? You do need to memorize the 8s and the polyatomic ions, right? Percent, whenever you see the percent always means the exact same thing. It just means part over whole times 100. That's really what percent means, right? If you take an exam and you get an 85, so if it's 100 questions and you get an 85 out of 100, right? You just got an 85%. Same thing in chemistry, part over whole times 100, right? So part over whole times 100, okay? So there's a formula, but you don't need to remember it. Just remember, it's just like when you take a test, part over whole, however many you got right, over the total times 100. So for example, let's look at this one, carbon. It's asking about the percent carbon. So it's just asking for your carbon over the whole times 100. We have 2 carbons, right? Where do we get the number? Periodic table, right? So we have 2, I'll just do it right here. So percent carbon, again, part over whole times 100. So 2 times 12.01 over the whole. I don't know what that is. 2 times 12.01 plus 4 times hydrogen, whatever that is, times 100. Part over whole times 100. That's percent composition. It's so simple. Part over whole times 100. It never gets any harder. This is it. This is as hard as percent composition gets. There's no formula to remember. Just remember percents like you've been doing. Every time you calculate a percent on a test or a quiz is the exact same way you're going to do it here. Just the numbers here coming from your periodic table. That's it. So again, this right here is 2 carbons plus 4 hydrogens from your periodic table. And you don't have to use AMUs. You can put grams here because again, remember grams and AMU, same thing. This is 1 carbon, right? If you use grams, you're just talking about a mole. It works the same way. You got 28 for the molar mass? I think you're right, actually, because carbon is 2 times 12 is 24 plus 4 hydrogen should be, right? 12 times 2 plus, well, let me just, so 2 times 12.01 plus 4 times 1.08. Yeah, 28 sounds way, yeah, that's right. You're right. Oh, shouldn't use this. This is from a book. It's wrong. Thank you. This is, I'm going to try to write it really neatly. Actually, I'm just going to write it over here. 28.052. 28.052. And so 24.022 divided by 28.052 is actually, good catch, Jose, 85.63%. You don't have to worry about sig figs here because I didn't give you any sig figs, right? Okay, so this also brings something that's very important here. Always use at least 2 places past your decimal. Always use at least 2 places past your decimal. Okay, so yeah, if you have a unit here, this would be 83% carbon. That's technically how you would write it. So carbon is 12.01. Don't round it to 12. Keep 2 places past your decimal. If you round your molar masses and you've got something big, it's going to make your answer far enough away that you're going to end up with a wrong answer. So always keep at least 2 places past. You can go more than 2 places past, but keep at least 2. Like for hydrogen, I always keep 1.008. Some people round that to 1, I don't. So that brings me to another point. When I'm doing problems in lecture, your answers might be a tiny bit different. Right? They might be a little bit off because let's say like my periodic table only goes 2 places past the decimal, but let's say you have your periodic table and yours says 12.011 for carbon, right? And I use 12.01. Like the difference is going to be there, but it's going to be super tiny. So as long as your answer is close, it's okay. But always keep at least 2 places past your decimal. You can go more, but keep 2. Okay, so now we're going to do empirical formulas. So when you've done empirical formulas, there's like a little process to it. Let me see. Trying to figure out where I can write this. Okay, so for empirical formulas, I'm just going to put it right here. So the first thing is you assume 100 grams. We're going to be doing this in class, by the way. You either assume 100 grams or they give you grams. Okay, like you need to get to grams. If they give you percent, you assume 100 grams. Second step is you go from grams to moles. The third step, let me try to write this neater. Divide by the smallest number. Sorry. And the fourth step, if needed, only if needed, multiply to get whole numbers. And we're going to go over what each of those are. So write this down because we're going to talk about this. So assume 100 grams, or if they give you grams, just start with grams. Convert everything to moles, divide everything by the smallest number, and then if needed, multiply to get whole numbers. All right, let's try it. So here is our problem. So this is in sunscreen, right? Which they've taken out sunscreen because it's not safe. And it says it's 61% carbon, 5% hydrogen, 10% nitrogen, 23% oxygen. What's the empirical formula? Okay, so when you do this, they're giving us percent. So we, number one, assume 100 grams. And so how I do this, so we have C, I treat it like a little conveyor belt because whatever you do to one, you do to them all anyway. So I just do them all at once and then I move on and do them all at once. So step one, assume 100 grams. So I've got 61.31 grams of carbon. And I've got 5.14 grams of hydrogen and 10.21 grams of nitrogen and 23.33 grams of oxygen. Phew. grams to moles. So like I said, I treat this like a little conveyor belt. I'm going to convert all of them to moles. So carbon is 12.01 grams of carbon in 1 mole of carbon. Hydrogen is 1.008 grams of hydrogen in 1 mole of hydrogen. Nitrogen is 14.1. Again, I'm getting these all from the periodic table. I just have a bunch of them memorized. And oxygen is 16.00 grams of oxygen in 1 mole of oxygen. So that's step 2, right? You see how I like to literally treat it like a conveyor belt. And then we put all these in our calculators. So when you put them in your calculators, I always tell people, don't round, like keep 5 digits. Trust me, I would keep like at least 3 digits. 4 is even safer. So 61.31 divided by, and I have some of these for you, so I'll just write them. This is 5.10491, 5.14 divided by 1.08, 5.0992, 0.7288, and this is 1.456. Okay. That one to one more digit. 23.33 divided by 16. 8. 1.4581. I don't think I'm going to believe the book on these answers right now. 728. I'm going to keep 1 digit more. You'll see why. 876. Again, don't round. This is the one time significant figures are gone from your brain. Like they don't exist right now. Okay, that was step 2. Step 3. This is the one everyone forgets. Divide by smallest number. Don't forget this one. Divide by your smallest number. Our smallest number is right here. Whatever you do to one, you do to all of them. Okay, well, this one had better equal 1. Better equal 1, right? One of them better equal 1. And then we start dividing. I'm going to start at the top. 5.10491 divided by 0.72876. This gives me 7.0049. 5.0992 divided by 0.72876. And I always tell people, do all these calculations twice if you have time, just in case. 1.4581 divided by 0.72876. Oh, this is lovely. 2.007. Okay, so these ones are close enough. This is definitely close to 7. This is definitely close to 7. This is definitely close to 2. So our empirical formula is going to be C, because it's C, 7, H, 7, N, there's just one of them, O, 2. That is our empirical formula. We didn't need to do step 4 because it all came out perfect. That was nice. It came out perfect for step 4. So this is our empirical formula. And again, I have it neater here. So does anybody have any questions? So here, this one was step, I'm going to try and keep it in the same color. This one's step 2. Where we convert them all to moles, grams to moles. And this one was blue. It's step 3. Divide by smallest number. And then here are our numbers. Okay, so any questions on these? So first, convert them all to moles. Go at least 4 places past your decimal. this is the book answer, you should always go at least 4 places. Just because if step 4 is needed, and I'll show you one of those, always go 4. And then divide by the smallest number, and then you get your periodic table. Your empirical formula. Okay, any questions on this one? Because we're gonna do something you haven't seen before, probably. Okay, no questions? The next one we're going to do is what's called a combustion analysis. So a combustion analysis is a super special empirical formula question. There's just one-ish extra step you've got to do. So what happens, remember in a combustion reaction, we always make CO2 and water, and we burn a hydrocarbon, hydrogen and carbon, and we make CO2 and water. Remember this? Right? We'll talk more about these later. And so the question is, if we have C's, H's, and O's, we burn it, and it always makes CO2 and water. Well, you can see, look, O is here and O is here. So how do you get the mass of O? Well, you can get the mass of C, you can get the mass of H, but O, you have to figure out in a very special way. So you need to figure out the mass of C and the mass of H, and then you can figure out O. So you can figure out carbon from CO2, hydrogen from H2O, then you do your oxygen. So I'm going to walk you through this. I'm going to try and do this as neatly as possible. Okay, so here we go. I'm going to try and make this as neat as possible. So this is burning butyric acid, which butyric acid is like the worst smell ever. It's worse than a skunk, literally. It's the worst smell ever. In excess oxygen yields 0.882 grams of CO2 and 0.36 grams of H2O. What is the empirical formula of butyric acid? So butyric acid, it's producing CO2 and H2O. So it might just be C's and H's, or it could be C's, H's, and O's. Like we don't know what butyric acid. So we just know like when we burn this butyric acid, and it combines with oxygen, it makes CO2 plus water. But this could be just C's and H's, or it could have O's. We don't know. We can't tell because the products have C's, H's, and O's. So we need to figure it out. So the first step that you do is you have to figure out how much carbon is there and how much hydrogen is in there. So first let's find carbon. So this kind of has like a multi-step process. So hopefully I've given you enough room to write this. Okay, so if we have 0.882 grams of CO2, we can get to grams of carbon, right? So if we have, we're going to get to carbon first. 0.882 grams of CO2, and I need to go to grams of carbon, right? So if I write this, we'll try to do this very neatly. The molar mass of carbon is 44.01 grams. Sorry, the molar mass of CO2. Again, I just added it from the periodic table. You'll have a bunch of these memorized. And in 1 mole of CO2, there's 1 mole of carbon, right? And I'm going to grams of carbon, right? So I need to get to grams of carbon. That's where I'm going. And you're going to see why in just a second. In 1 mole of carbon, there's 12.01 grams of carbon. So hopefully we're all okay with this conversion. If not, we'll keep working on it. But the first thing we have to do, get grams of carbon and grams of hydrogen. That's what we got to get to. You're going to see why in a second. So 0.882 times 12.01 divided by 44.01, just making sure that everything's right. And I get 0.24, I'm not going to care about my sig figs till the end, 0.69 grams of carbon. Now I need to get to grams of hydrogen. We're going to do it the same way. We're going to get it from water. 0.360 grams of water. And the water is 18.02 grams. grams of water in 1 mole of water. Again, just got that from the periodic table. In 1 mole of water, there's 2 moles of hydrogen because there's 2 hydrogens. And then in 1 mole hydrogen, there's 1.008 grams of hydrogen. Right, grams, moles, moles. Because we need to get to grams, we need to get to grams of H and grams of C. So 0.360 times 2, 0.360 times 2 times 1.08 divided by 18.02. I got 0. Let's see why I'm trying to make this neat right here. 0.0402, I don't know, 7 grams of hydrogen. Okay, so now got to grams of hydrogen, got to grams of carbon. This is the extra step that you have to do before you can actually do an empirical formula when you've got a combustion. The reason is because we don't know if there's oxygen in this, right? We don't know if there's oxygen in butyric acid yet. There might be, but there might not be. So what we do know is that our sample is 0.44 grams of butyric acid. So if butyric acid is C's and H's only, when I add this up, it should equal 0.440. If there's only C's and H's, it should add to 0.440. So let's try. Plus 0.24069. I get 0.28096. And again, this is grams of C and grams of H. This does not equal 0.440 grams of our butyric acid. Our butt acid, right? So that means we have C's, H's, and this is C's and H's, this is CH and O. So this must have CH's and O. So question for you, how can I get the grams of oxygen? What can we do? How can I get the grams of oxygen from here?
Subtract it.
Go ahead.
Subtract it.
Yep, exactly. So to get to my grams of oxygen, it's going to be 0.440 grams, and this is going to be C's, H's, and O's minus 0.2809. Probably went a little crazy with the calculator here, grams of C plus grams of H. When I subtract it, it's going to give me grams of O. So 0.440 minus 0.28096. 0.15904 grams of oxygen. This is the extra step we have to do. So now, if when I added these two, let's say it gave me 0.440, well, that means I only have C's and H's and I can just keep going. But if it doesn't add to this at the beginning, that means I've got O's, right? And so this is the extra step that we have to do with empirical formulas with combustion analysis. We have to check, hey, are there O's? And the reason is, again, because oxygen is in both CO2 and water. So we need to say, like, is the oxygen just from the air, or did we actually start with oxygen? So now it's a regular empirical formula problem. There's just this extra little piece here. So I think I started this with red. I'm going to try and keep this the same. And so really at this point, you can just, you're at grams here. So some people will just go, okay, I'm going to go to my grams here and like finish this. That's fine. Really, whatever you want to do. I'm just going to do it here to keep it separate. It's kind of redundant. So if I have C, H, O, now we're just doing the same thing. So 0.24069 grams of carbon. I'm going to convert it to moles. Oops, hydrogen is 0.04027 grams of hydrogen, converted to moles. Oxygen is 0.15904 grams of oxygen, converted to moles. There, 0.0 grams, 1 mole. Right, that was our step 2. So 0.24069 divided by 12.1. This gives me 0.02004 and 0.04027 by 1.08. I hope other people are doing this too, because I make calculator errors all the time, just like you do. And I always say, like, go 4 places, like, just to be safe. 0.15904 divided by 16. Most one just put it straight into scientific notation for me, that's fine. Into the negative, that does not look like a 3. Okay. Our next step, I did in green, which I can't change my color anymore, right, is divide by the smallest. That's going to be our oxygen over here. You can see these are a little bit on the long side. Right, this one had better equal 1, and better equal 1. 0.03995 divided by 9.4273. 4.019. Oh, that's kind of on the border. Actually, it's 01, so we're good. 0.0204 divided by 9.94, and to the negative 3. 2.0160. So we can round this to 4. It's pretty simple. We can round this to 2. And so our empirical formula ends up being, just going to put it here, C2H4O. So it did have an O in it. Okay, so this is the empirical formula. Really quickly, I'm just going to talk about the molecular formula. The molecular formula is pretty simple. So for molecular formula, you just do me. I call it me. The molecular formula, molar mass, over the empirical formula, molar mass. Me. Now, the molecular formula, molar mass, is always given. $88 given. Empirical, you have to add, right? So 12.01 times 2 plus 4 times 1.008 plus 16. 44.052. And when you divide that, you get 2. That's the molecular formula, is this one tiny little extra baby step. What does this mean? It means multiply everything by 2. So that means instead of C2, it's C4. Instead of H4, it's H8. Instead of O1, it's O2. Molecular formula. Empirical formula. So I'm sure everyone's done this before. It's just probably been a long time, right? Oh, so, oops, hold on. This came from adding this right here. So I just added from the periodic table. Periodic table. So just adding from the periodic table. So yeah, super great question. Okay, any questions on this before we go? Because I know some people have to get to class. This is a big one, right? It's a big one. It's just got that little extra piece in the beginning, which we know how to do the extra pieces. We just have to put it all together, right? So this is, again, anytime when it says like burning or combustion, you gotta go through all of this for your empirical formula. And you'll be practicing this a lot in Chem 101 too. Okay, so